Let's talk about the analysis of algorithms. The analysis of algorithms measures various parameters about how an algorithm works. Of course, one parameter which we cannot sacrifice is correctness, and we assume that any algorithm we design will be shown to be correct in that it will always compute the answer that is expected of it. Another desirable property might be simplicity. How easy is it to understand an algorithm? Now, as you might expect, this varies according to the person who's trying to understand it, and it's kind of hard to measure or quantify. So what analysis of algorithms typically focuses on is something that can be quantified, and this is what we call efficiency. So efficiency tells us how much the algorithm consumes by way of resources. The two most important resources that we will look at are time and space. Time, of course, is running time. How long does the algorithm run before it produces the answer we want? If an algorithm is very slow, then we may not be able to get useful answers to our problems in the time that we have available. The other resource is space, which is typically in terms of the memory. How much auxiliary space or auxiliary storage does our algorithm need to compute the answer we want? Once again, if it requires keeping track of too much information, then the resources we have at our disposal may not permit the effective solution of a problem. Now, the reason it is important to understand how efficient an algorithm is because when we look at algorithms across hardware, as hardware improves, we find that the efficient algorithm will always beat an inefficient one, no matter how much the hardware improves. So you might argue that an inefficient algorithm today will run faster tomorrow, but so will an efficient one. And as we shall see, there is an order of magnitude difference in the size of problems that efficient algorithms can handle with respect to more inefficient ones. To get a feel for this problem, let us look at a concrete example. So let us take the example of sorting. So we have a list of numbers and we want to rearrange them in sorted order, maybe in ascending order. So for instance, we might want to create the following list out of this. Now there are inefficient algorithms and efficient ones. So the inefficient algorithms will take time proportional to n squared, where n is the number of elements in the array, and the efficient ones will take time proportional to n log n. Okay, so n here is the size of the array. So now the question is, can we really see the difference between n squared and n log n? So we can do this by working out some kind of numerical values. Now a typical CPU, say a desktop, can do something like 10 to the 10 operations per second. Now we won't worry about what is an operation, but we are really kind of discussing the basic steps that an algorithm can take. So if we are saying that something can do 10 to the 10 steps per second, and if n squared is 10 to the 10, then it will get done in 1 second. If n log n is 10 to the 10, it will get done in 1 second. Now we should actually keep in mind that this is sort of optimistic, and we should really think of something like 10 to the 9 or even 10 to the 8. But 10 to the 10 is okay for calculation purposes. So let's assume that we can do 10 to the 10 operations per second. So now I look at an input, say, of size 10,000. Okay, and this is of course 10 to the 4, and so n squared will be 10 to the 8, and n log n. So now n log n you have to check. So a log of it. So this is usually log to the base 2, although you can take log to the base 10 if you prefer. So log to the base 2 of 1,000 is 10, because 2 to the 10 is 1,000, and this is 10 times that. So it's basically log of 10 plus log of, so log of 10,000 is log of 1,000 plus log of 10, because logs add, and so this would be roughly 13. Okay, so this means that in order to sort an array with 10,000 elements, an n squared algorithm would take 10 to the 8 operations, and n log n algorithm would take something like 13 times 10,000. So this would be roughly 10 to the 5 operations. Okay, and so both of them will be comfortably under 10 to the 10, and so both of them will terminate within 1 second. So if we had small inputs, and by those 10 to the 4 may not seem small, as we will see, it is small from a practical point of view. For small inputs, really you would see no difference. Okay, so small inputs, n squared and n log n are equivalent. from the user's perspective. Of course, they're not equivalent as algorithms, but from the point of view of the user, you will not see a real difference because both of them will terminate almost instantly. So what do we have a larger example? So what would constitute a larger example? Okay, so a typical larger example is something that happens with real life data. For example, if you say voters list, right? So we have all these enumerators going around door to door and they collect a list of all voters in the city. And now let's assume that we have a really big city. So we have something like 5 million voters in that city. And then we have to publish a list. So in order to publish the list, we have to collect all the data from all these different voters and then write it out in some reasonable order. So in some form or another, we have to sort it. Okay, so we have 5 times 10 to the 6 voters. Okay, and now if I take n squared time, okay, I'm going to take 25 times 10 to the 12 steps, okay, roughly, and assuming 10 to the 10 is what gets done in 1 second, this would mean something like 2500 times 10 to the 10. So this is 2500 seconds, okay, and 2500 seconds, if you divide by 60, you get that this is going to be something like 40 hours. Okay. On the other hand, n log n, as we saw before, is going to take 10 to the 6, which is n, and log of 10 to the 6 is 10 to the cube, 10 to the cube, so it's about 10 plus 10, 20 times 25, and so this is going to be well under 10 to the 10. Okay, so this is going to be 1 second or less. So if we have this voters list with 5 million voters and we try to sort it using an n squared algorithm, it takes us 40 hours. If we try to do it with an n log n algorithm, it takes us 1 second. So you can see an enormous amount of usability trade-off between an inefficient algorithm and an efficient algorithm, which you don't really see for small inputs. So this is basically one of the things that we will look at. We're really interested not for tiny inputs. So tiny inputs, everything works pretty much the same. We're really interested in what happens as inputs get large. And in practice, because data is large, really these algorithms will be used on large data. So though we may not on our desktop typically have a list of 1 million items to sort, if you're really dealing with real world data which you need to organize, this is not an unreasonable answer. Okay, so one may argue that sorting a list, a voters list for example, is what we might call an offline activity, right? So we do this and then we publish the list and then we don't have to worry about it ever. So okay, so if it takes 40 hours, so if it takes a couple of days to get the list ready, it's perfectly fine. So is this a valid reason to switch to an n log n algorithm? Because after all, this is a one-time activity which can be done infrequently and we can spend some time on it. So let's look at another example. Okay, another example that I will look at is some kind of a video game. So I don't have a specific video game in mind, but let's assume that you're playing a video game on a screen. Okay, so you have a screen like this, and on the screen you have lots of obstacles, dots, players, various entities which are positioned on the screen, right? And at various points in the game, one of the problems might be to determine which pair of these entities is actually closest to each other. Right? So which is the pair, which is the closest pair of points? Okay, so these points could be, as I said, they could be players, they could be opponents, they could be inanimate obstacles. We don't really care, but let's assume that this is what we need to do. So we need to quickly find out which pair is closest to each other. So a naive solution would be the following. So you take this screen, right? And then you have these objects on the screen, right? And so you pick every pair that you can find. So you pick this pair and you compute its distance. You pick that pair and you compute its distance. You pick this pair and you compute its distance, and so on. So the naive solution here is compute d for every pair and then choose the minimum. Right? So let's assume we have n objects. Okay, then we have n into n minus 1 by 2 pairs. Right? This is nothing but n choose 2. Right? So we have about n squared pairs. So what we are really doing, like our sorting, inefficient sorting, is we are doing an n squared computation in order to determine which pair of objects is closest to each other. Now remember, we are doing this in a video game. Okay? So in a video game, we can't spend 40 hours doing this. So how long is this actually going to take? So let's take some numbers again. So let's assume that we have a kind of high resolution screen. So maybe we have a screen which has 2500 by 1500 pixels. Okay, so this is not unreasonable for a large, say 29-inch monitor or something like that. Okay, so if you multiply this out, we have something like 3.75 million pixels. Okay, so I'm going to, for now, assume it's 4 million. So it's 4 times 10 to the 6 pixels. Okay, so in this, it's not unreasonable when I have 4 million pixels. Maybe I have something like 500,000 objects. Okay, so that's 5 times 10 to the 5 objects. Okay, so this is actually my n, right? So n is 5 times 10 to the 5. So now I run this inefficient algorithm, which is n squared. Okay, and I'm going to get 25 times 10 to the 10, right? So remember the 25, so this is what happens in 1 second. Okay, so this is going to take me 25 seconds. Okay. Now 25 seconds of course is much better than 40 hours, but imagine if you're sitting in front of a video game and then it has to compute this in order to let you continue, and it actually makes you wait 25 seconds to say, oh, I'm updating positions, I'm updating the score and so on. This would be a totally unusable game, right? So here n squared would really hit you in terms of immediate response. At the same time, there is an efficient n log n algorithm for this closest pair problem. Okay, so it uses a technique which you will see later called divide and conquer. So what it will do is it will kind of divide the screen into two parts, and it will find the shortest distance on this side, it will find the shortest distance on this side, and then it will combine this answer. Of course, now there may be distances across this boundary which have to be computed. So there's a clever way of doing all this so that it takes time n log n. And n log n, if n is are 5 times 10 to the 5, so n log n is going to be approximately 10 to the 7, and this is going to be no problem at all. Okay, so we have something which again works in a fraction of a second, so it's like 1/1,000,000th of a second if we are assuming that 10 to the 10. So we have 1 millisecond to compute this, and of course 1 millisecond is something that as a user of this video game we would not worry about, because that is certainly less than our reflex time in actually playing this game. So hopefully with these two examples you're convinced that efficiency matters. Okay, so efficiency does matter from the point of view of the usability. So from the usability point of view, it is important to have a more efficient algorithm no matter what, because no hardware scale up can actually compensate for these huge differences in order of magnitude between what an n log n algorithm can do in these examples and an n squared algorithm can do. Okay? Now there is another important reason to have efficient algorithms, or rather it's not a reason to have efficient algorithms, but an outcome of developing an efficient algorithm is a better insight into the structure of a problem. This may not always happen, but it does happen quite often. So for instance, if you look at sorting, okay, so the real question in sorting is compare and order all pairs, right? So we want to know for every pair of numbers in the input which is smaller, which is bigger, okay, and all pairs. So since it is all pairs, this becomes n squared, because there are, we saw, n into n minus 1 by 2 pairs. On the other hand, we can use obvious information that if A is bigger than B and B is bigger than C, then we can conclude that A is bigger than C without checking, right? Because we know that this bigger than relation has this what is called transitivity. If A is bigger than B, B is bigger than C, it must be that A is bigger than C. And so we can have sorting algorithms which exploit this. They don't make unnecessary things, right? So you avoid unnecessary comparisons. So this is an insight that we need, that the comparisons we are doing have this property that some comparisons imply other comparisons. And so if we avoid unnecessary comparisons, we are actually able to bring this down to n log n, right? So in addition to just the user's perspective, it's also aesthetically and mathematically important to look for the best possible algorithm, because often the problem itself might admit some structure in it which gets exposed as you get better and better algorithms. So typically the inefficient ones are called brute force. What is the first thing that you would do exhaustively by trying out all possible combinations? Then you develop some insight, aha, if this happens then that cannot happen and so on. So you start building up a mathematical model of the problem which gives you a much better insight into what the problem is about, and as a result gives you a better algorithm.